Yeah. I'm not gonna say that. No, I'm not sure. I'm gonna take physics. I take like 1 second. That's fine.
What did you come? I
I'm gonna have like next year. I think these like.
What makes you think?
All right, page 20. So today we're doing something called the first derivative test, using the first derivative sine line to help us get a picture as to what the graph could look like. Now, I think this procedure, you already are pretty familiar with this because we've been doing sine lines for velocity, and this is basically the same thing. It's just now from a visual standpoint in terms of how the graph is rising and falling instead of moving left and right along the horizontal line. But the process will feel essentially the same. Okay, so all right, so what does the derivative represent? Derivative represents the slope of the tangent line to the function or the curve. A function is increasing when my derivatives are positive, right? So when f prime is greater than 0, that means my slope is positive. If my slope is positive, my graph is going to be rising. Right? And we always read the graph from left to right. And we always associate slope from left to right. But when the function is decreasing, what's common about the derivatives at those points? F prime is going to be less than 0. When f prime is greater than 0, the function is increasing. When f prime is less than 0, the function is decreasing. When f prime is 0, then we know our function is constant. So either there's a horizontal or a change in direction. So there's two instances or a couple. It could be either a valley of the graph, it could be neither, or it could be the peak of the graph, right? So these are all places where slope is 0. So slope 0 is a candidate for a max or min, but it's not guaranteed to be a max or min, right? Just because slope is 0. But we do want to always look for slope 0 because we want to find the candidate first, and then we'll test the candidate with the sine line. So here's the first derivative test. We're going to find f prime set equal to 0, very much like how we do with particle motion, right? We find velocity, we set velocity equal to 0. Find critical points, right? So we set f prime equal to 0. Solve for x, just like how we did with velocity. But make sure that we look for critical points from both the numerator and denominator. Okay. Sometimes we may be coming across vertical asymptotes, but we still want to look at the denominator because even though a vertical asymptote has no chance of being a relative max or relative min or peak or valley of the graph, it can still be a place where we can separate our intervals. Okay. Remember, critical points also exist when a function is not differentiable. So sharp turn, sharp point is also considered a critical point. Okay, so what we're going to do is we're going to plug values into f prime to determine the slope. A positive slope means the graph is rising. A negative slope means the graph is falling. And we're also going to learn how to write because statements. Okay. If a function is increasing, we say because f prime is greater than 0. If a function is decreasing, we want to say because f prime is less than 0. A relative max, okay, we can say that there is a relative max because f prime changes from positive to negative, and a relative min because f prime changes from a negative to a positive. Okay, so the process that we're going to go through is going to feel very much like what you've been able to do on the previous quiz with particle motion. So let's look at number 1 here. Determine the intervals at which the function is increasing and decreasing. Locate relative extrema. So locate relative max, relative min. We'll go through the full process here, but everything that we need is basically going to come from the f prime, mostly. Okay, mostly. Okay, so let's find f prime first. Everything is set up nice and ready for power rule. Okay. What's the derivative of the first term there? Okay, yeah. I'm going to just do the full thing, but you can definitely skip this step. Plus minus 6. Okay, so there's no denominator to worry about. We can just set the whole derivative equal to 0, and we can start looking for critical points by factoring. Multiplies to be -6, adds up to be 5. Solve for x. Right, feels like the same thing that we're doing from particle motion, right? So now we're going to create a derivative sign line. Place all of our critical points onto our derivative sign line. And we're now going to choose numbers in each subinterval to test. And the whole purpose of these numbers is just to figure out what the signs are. I like to put it into the factored form of the derivative. All I care about is the sign. Okay. So -7 plus 6, positive or negative? Negative. -7 minus 1. 2 negatives make positive. So it's going to be a positive slope here. What I like to do is I like to have just a visual reminder how the graph is going to look. So I like to draw an arrow like this to indicate the flow of my graph. My graph is going to be rising in this interval. Okay. All right, so 0 in for x. 0 plus 6, positive. 0 minus 1, negative. So negative. And then to show how my graph is moving, I like to draw an arrow decreasing like this. Gives me a nice visual as to how my actual graph is rising and falling. Okay. All right, 2 in for x. Positive and positive. Yeah, so back to positive. So as a reminder, do not use these test numbers for anything else, right? So the whole purpose of those test numbers was just to populate, figure out the direction of motion, but when you write your intervals, do not include the -7, the 0, or the 2, right? You're just using -infinity, -6, 1, and infinity. So let's just visualize what this graph is doing, right? The graph is going to rise all the way until some y value when it hits -6. And then it's going to fall. So what do you expect at -6? There's going to be a what there? Relative max, right? And then the graph is going to fall until some y value at x equals 1. Then it's going to start rising again. We expect a what? Relative minimum. Yeah. So what about your interval increase decrease, right? Where's your graph increasing from? Negative to -6. Yep. And then also from 1 to infinity. We use brackets for all these intervals. Okay, parentheses for all these intervals. And then where's the graph decreasing? -6 to 1.
On the AP problems, I saw like a bracket.
Yeah, I think there is a even on the AP pre-calc, they're kind of going back and forth between brackets and parentheses. So I think you make an argument for bracket, but I just always say parentheses because there's never any issues with grading, losing points. We can use parentheses in the bracket. So I just always say parentheses. But maybe now they're allowing brackets, but I feel parentheses is the safer way to go. But if you put brackets on my test, I won't take off points, but I do want to encourage you to use parentheses. Okay, so now what if I want to find the physical point of this relative max? Plug into the original, right? Okay, plug into the original. What if I want to find the relative minimum order pair at 1? Plug into the original as well. Okay. Sometimes they would ask you, the problem would ask you for just the x value. Sometimes they would ask you for the full order pair. So just know where to find that information, right? Anything that is location related comes from the original function. Anything that is slope related comes from the first derivative. Okay. All right, so we're going to see if we can practice writing out all of our statements, including the because statements. Okay, so on the test, I'll be looking for these because statements. Okay, so see if you guys can go ahead and write those down. All right. We're just writing down what you've already expressed to me verbally. Pay attention to those because statements. And the 51 and the negative 6.617, those came from plugging in these x values into the original function. Okay, I'll leave this up here for another moment, but go to page 21. Determine the intervals in which the function is increasing and decreasing. So we know anything that's involving increase, decrease has to come from the first derivative. But look at how example 2 is set up. We got to go through what? Quotient rule. Yeah, so let's find the derivative using quotient rule. And then once you get everything nicely cleaned up into a nice rational function expression, then you're going to set your numerator equal to 0, set your denominator equal to 0, and anything that you find, you're going to place onto your f prime sign line. Okay. I'll walk through the steps, but give you guys a head start if you're done with this page. Okay, f prime g minus f g prime all over g squared. All right, anybody still need this page? I hope to get back your tests tomorrow. They are in the grade book already. But as I was grading, I did notice one thing is that, some of you guys would reference quotient rule, but then this happens a lot, not happens a lot, but it's easy to forget that there's a denominator portion of quotient rule, right? So just don't forget that some of us were leaving out the denominator portion when you went through quotient rule. So okay, distribute that 5 through, distribute the -1 through, combine like terms. Okay. We'll set the numerator and denominator equal to 0. Anything from the numerator? No critical points, right? There's no variable there. So we looked, we didn't find any. Is there a critical point from the denominator? There is, right? Now, what's the critical point? X equals 3. Now look back at the original problem. What do you know about x equals 3? It's a what? It's a vertical asymptote. So you know that there's no chance that this could be a relative max or relative min, right? But we're still going to go through our f prime sign line. We still want to know the behavior of the slopes on either side of that 3. Okay, so create your velocity sign line. Sorry, not velocity. Your f prime sign line. Place 3 onto your sign line. You can test numbers on either side of 3 back into the what? Derivative. Yeah, you want to test with your derivative because you want to find information about slope. So if I plugged in, let's say, a number less than 3, like 0, numerator will give me negative, denominator is positive, so negative. So I know the graph is going to be falling to the left of 3. But if I plug in a number greater than 3, I'm still going to get what? Still negative, right? Yeah, still negative slope. That -17 is always staying -17. The denominator is always positive. So my graph has no relative max, no relative min, but it does have intervals of decrease. But we do need to split them up because we can't include 3 as a place where the graph is decreasing since the graph doesn't exist there. So we say our function is decreasing on the 2 separate intervals because f prime is less than 0. And they say to locate relative extrema, we do not have relative extrema for this function. Okay, we'll skip example 3. I do want to dedicate a day to talk about derivative graphs and how to interpret derivative graphs. So we'll skip that and come back. We'll do a whole lesson on that later. Okay, let's go to page 22. Okay, concavity test. I think a better word for that is this test for concavity. And then there's also something called the second derivative test, which I'll go over later, but I'll focus on this for now, test for concavity. So what do you, what's similar about all the slopes on this curve? Always increase. Okay, yeah, that's, but what's also similar is that they all have positive slopes, right? Positive slopes, but like you said, the slope is increasing, right? So maybe this is a slope of 2 or 1/2, then it goes to, 1, then 1/2, then 1.5, then 2, 2.53, right? So my slope is continually increasing, right? Or it's becoming more positive. How's that? Yeah. How about this one here? The slope is also all positive, but the slope is becoming less positive. So here we can say that the rate of change of the slope is increasing. Right? And here we can say that the rate of change of the slope is decreasing. So basically this refers to a second derivative, right? It's asking, this basically showing the rate of change of the slope, right? Or the second derivative. So these functions, they're both increasing, yes. We know about their derivatives. Their rate of change of slope is changing. Or the rate of their slope is changing. Either in one direction or the other. So we have something called concave up. And concave up has this shape, but also has a very interesting relationship in terms of the slopes at every point on the concave up graph, is that your slope is always becoming more positive. Or your slope is always moving in the positive direction. And I just want to demonstrate that to you. We're going to just do some we're just going to ballpark these slopes. So let's say this is a slope of -4. Then it becomes, let's say, -3, then -2, then -1, and eventually it's going to become what? 0, and then it starts becoming positive 1, 2, 3, 4. Now look at the pattern of these numbers. Do you agree that these numbers are all becoming more positive? They're moving in the positive direction. So if you can imagine these are numbers on the number line, you're just moving to the right of the number line the entire time. That makes sense. Okay, so if you can convince yourself of if the slope is going to move in this direction, it's always going to have that up that concave up shape. Meanwhile, if a graph is concave down, your slope is becoming more negative. So maybe we start off with a steep slope of 4, then it goes to 3, then 2, then 1, then 0. And then you can imagine the slope becoming more and more negative. So from left to right, you can see that these numbers are definitely moving in the negative direction. If you're placing these numbers on a number line, you're always moving left, right? So if my second derivative is positive, that means my slope is increasing or becoming more positive, and that way I can conclude that my function is concave up. If my second derivative is negative, that means my slope is becoming more negative, is moving that negative direction. It's going to create this shape, and the shape is concave down. Now, we also have this point of inflection. Point of inflection is kind of like a transition point of your slopes. This is where your f double prime changes sign. This is where also you change concavity. So for instance, let's say I had a graph that looked like this. Okay. And I'm just going to ballpark these slopes here. Let's say it's 3, 2, 1, 1/2, 0, -1, -2, -3. -3, -2, -1, 0. Do you see how these slopes are going to eventually turn around and start moving in the other direction? You see that? So this is what we call a point of inflection. So imagine these are numbers on a number line. If you can see yourself with these slope values, you start turning in the other direction. We call that a point of inflection. And this is where your second derivative function is going to equal to 0. That's where your rate of change of these slope numbers are going to become 0, right? So imagine you're walking back the other direction on that number line. So the test for concavity is helpful because we can now gather more information about the shape of the graph. We may, from first derivative test, we know whether the graph is rising or falling, but if we can get information about concavity, we can get more detail about the curvature of the graph. How is the graph curving along those paths? Okay, so the first thing we do is we're going to set f double prime equal to 0, very much the same steps as f prime, we're just doing it one derivative lower. And then we're going to find these critical points from both numerator and denominator. We're going to find these critical points, and we're going to place those critical points onto our second derivative sign line. So let's say I found A and B. And just like before, we would test numbers in each subinterval, put it now into the second derivative because we're trying to gather information about concavity. And let's say I got a negative number. If I got a negative number, then I know the graph is concave down. Now, the shape that I want to use is this concave down shape as a reminder how the graph is going to be shaped in that interval. Okay. And let's say from A to B, my concavity is still negative, so I would still represent that as negative. And let's say to the right of B, I get a positive. So concave up. Now, I purposely made it a situation where two had the same signs and the other had the change in sign. This A is a candidate for point of inflection, but it is not an actual point of inflection because there is no change in sign. It has to change from one concavity to the next in order for it to be a point of inflection. So B, in this case, would be a point of inflection because F double prime changes signs. We don't have to specify the direction of sign change. You know how relative max, relative min, we got to say F prime changes from negative to positive, or F prime changes from positive to negative. You can, it wouldn't be wrong if you want to specify the order of sign change, but it's sufficient enough to just say F double prime changes signs to justify that you have a point of inflection. Point of inflection may exist at, F double prime does not exist at a sharp point, but point of inflection can still exist if that sharp turn has a change in concavity on both sides. Okay, so let's look at example 1. It says find the point of inflection, and also let's also find intervals of concave up and concave down. Now, eventually, we're going to see some problems where we're going to put it all together, increase, decrease, first derivative test and second and test for concavity all onto the same problem. But this one, let's just move directly to the second derivative and just do the second derivative and practice with that. So we'll go to F prime, but we're not going to do anything with the first derivative test here. Okay, what's F prime equal to?
4 plus 5 is good.
Okay. The threes cancel out, right? Right. We'll move on to the second derivative since we just want practice with concavity information. Okay, keep going. Second derivative, we get. Okay. There's no denominator to worry about. We can just set the numerator equal to 0. What's the GCF that we can factor out? I'm going to say negative 10x, but it's the same thing. You can just adjust if you want to. You can either solve for x here or I can continue factoring. It's up to you. But either way, we're going to get 3 critical points. Okay, we're trying to determine the behavior of the curvature of the graph. So any test number that we find and we use, we're going to insert into the what? Second derivative, right? Second derivative. We're not, at this stage, we're not concerned about the slope. We're concerned about the curvature. Okay, so I chose -1, -1/4, 1/4, and 1. I'm going to insert into either of these two, whichever you want to do. All right, so I plug -1 in here. I get -10 times -1. That's positive. And then 4 times 1 squared minus 1, that's positive as well. So everything is positive there. So I'm going to indicate that with positive, and then I want to have a reminder in terms of visually what's happening. There's going to be a concave up shape in that interval. You plug -1/4 in, negative times negative, again, that's positive. If I do 1/4 in here, 1/4 squared is going to be 1/16. 4/16 is 1/4 minus 1. That's a negative there. So negative times positive is negative. Plug 1/4 in, negative, positive, negative. So 2 negatives make positive. Okay, plug 1 in, negative, positive, positive. There's only 1 negative. Okay, how many points of inflections do you see? 3, because there's a change in sign. Okay. Just want to kind of point this out, this as a side note. If a problem like this shows up on the AP exam, I would see this will be like a multiple choice question. It'll ask you how many points of inflection would you see? And what some students would do is they would solve for X, and once they solve for X, they just count these as points of inflection. Now, are these going to be guaranteed to be points of inflections always? All right. So you got to make sure you create your sign line and convince yourself there's a change in sign. So sometimes on the AP exam, multiple choice question would be, there'll be more candidates than actual points of inflection. So make sure you go that one extra step, test the signs, convince yourself there's a change in sign before committing to that candidate be a point of inflection. So just pointing out something that that I've seen. Okay, we can write all of our statements. Oh, and also, if I want to find the full ordered pair of my point of inflection, where would this go? To the original, right? Back to the original, because if I'm asking a physical point on the graph, it's got to go back into the original. Okay. So just understand when and where you want to involve the different functions, right? If you're testing the signs on the second derivative sign line, you're going to be testing these values against the second derivative function. But if I want to find the physical location of these points, they go back into the original function. Okay, so here are your statements of concave up and concave down, as well as your justifications, your because statements. So all the intervals of positive will be concave up. All the intervals of negative will be concave down. And pay attention to those because statements. Yeah.
You're right. F double prime is concave up, concave down is right. F of X.
Oh yeah, you're right. F double prime is, yeah, you're right. F double prime is positive, but I should really say f of X is concave up. My function is concave up. Thanks. Okay, one more topic I want to go over. It's called the second derivative test. It sounds like what we just did is called the second derivative test, but it's not. What we just did is called the test for concavity. The second derivative test is doing the same thing as the first derivative test. It's defining the relative max and min using the second derivative function. Okay, so go to page 23.
It's nothing to define the route. It's just another way.
It's another way. Yeah, it's another way. But I also want to show you that sometimes AP exam problem would present the problem in a way where you have to have knowledge of second derivative test to answer the problem. So, but yeah, I think to your point, if you had a choice, you would just usually choose first derivative test. It just feels more straightforward. But okay, here we go, page 23. The second derivative test is a test for relative extrema, not a test for point of inflection. Okay, for point of inflection, we call that the test for concavity. So ultimately, the second derivative test achieves the same result as the first derivative test. So you know how with first derivative test, we find f prime, right? We set f prime equal to 0. Okay. And then the third step, we would create our f prime sign line, and then we would go and test each of our candidates that way. Okay. The difference with second derivative test is that we are still going to find f prime. We're still going to set f prime equal to 0. We're still going to find our critical points, but we have a different way of testing it rather than putting into the sign line. Okay, what we're going to do is we're going to insert the critical points into the second derivative function and see if we get a positive value or if we get a negative value. And then we're going to use that to help us determine whether there is a relative max or relative min. Okay, let me show you what I mean by that. Let's say we found that 1 was a critical point. Okay, and we knew that f prime of 1 is equal to 0. Okay. So what, just from this information alone, what does that tell you?
Slope is 0.
Slope is 0. Now, if slope is 0, it could either be this, it could be this, or it could be that, right? We don't know what it is. Is it a relative min? Is it neither? Or is it relative max? Right. So we're kind of sitting at a spot where we don't know. We know slope is 0, but there's a lot of options that can happen, right? Now, what if I told you that f double prime of 1 is greater than 0? What would that mean as from a shape perspective? But in terms of a shape, what does this mean? This means that my second derivative at 1 is greater than 0. What does that mean? That means it's concave up. So where do you see concave up on this graph? Here, right? So if I can pair this information up, if the slope is 0 and it's part of a concave up graph, this point must be a what?
Oh,
Relative minimum. So that's the reasoning behind second derivative test. We're not using a sign line. We're using the shape of the graph to help us conclude whether we have a relative max, relative min. Does that make sense? Okay. Now here's where it's easy to be thrown off. When we see this positive value, the tendency is we think, oh, positive, that must be bigger, so that must be a relative max. Okay, so sometimes it's easy to get those two mixed up. But if you can verbalize this as concave up, and if you can visualize concave up, then hopefully that will be enough to convince you, okay, that's not a relative max, that's a relative min. But I just do want to point out that it's easy to get these mixed up because that positive can throw us off and think we may think maximum because it's positive and negative is minimum, right? That's opposite. Okay, so likewise, let's say f prime of 2 is also 0. But let's say we're able to plug f double prime of 2 or 2 into the f double prime, and we're able to get a negative in return. So that tells us that this has a slope 0, but it's also part of a concave down graph. The concave down graph looks like this. And the concave down looks like this. There's only one place for slope 0 on the concave down graph, and it's up here. And that is a what? Relative max. But when we see a negative number here, we think, oh, that's a small number, so it must be relative min. So, things like this can throw us off. If we see, let's say f prime of 2 is equal to 0 and f double prime of 2 is equal to negative 61, that's confusing, right? You're thinking, oh, wait, that's a really small number. That must be a relative min, but that is telling us it's concave down because it's negative. And then if you can verbalize concave down, you can convince yourself relative max. Likewise, over here, if it was f double prime of 1 is equal to 83, right? That positive number may throw you off because that's such a large number. That must be a relative max, but that's concave up. Concave up looks like this. That's actually a relative minimum. Okay. So I just want to point out the places where it's easy to get thrown off, and hopefully you can avoid that.
Whether you're.
No, usually with curve sketching, it'll just be X.
Okay.
And if it's particle motion, it'll be time. It'll be very clear.
Okay.
Yeah. We won't mix those up. Okay, I didn't quite do a full example, but I think we understand the process. I'll finish this up tomorrow. You guys do have homework from 5.3. Check your calendar, and I will make sure to load the AP problem solutions on the website. All right, come get your phones. Help sessions in the afternoon. If you are interested.
Yeah. They don't work, so is that like? So all I do is just watch it. It's not like it's like that's you need to think more.
Oh, I just like Mark this or they drop my stuff off.
You give me like 4 minutes to
Yeah, like stuff.
I kick it in the back. I'm missing all of those. So it's all fine.
So now I'm just like, oh, that's, well,
It's.
I can't miss.
Yeah, that's-
The day of. That's my thing.
Yeah, it's.
Yeah, well, you can.
Maybe it's the side view.
Oh, well.
When you start there, you'll put your book back in. Yeah. But yeah, whenever you're ready.
But should I, or would it be possible for you to count this?
Yeah.
Right here.